Hello, my name is Beatriz Castillo-Téllez, and I'm presenting the fish waste drying for fertilizer. My colleagues in this work were Margarita Castillo-Téllez, Marta Fabiola Martín del Campo, Gerardo Alberto Mejía Pérez, and Alfredo Domínguez Niños. We work in the Universidad de Guadalajara, in la Universidad Autónoma de Campeche, and in the Universidad Nacional Autónoma de México.
Well, first of all, I will start with a little introduction where I will explain why we choose these species, um, why they are so important in Mexico and some other stuffs, the methodology and the instrumentation that we use in this study, the kinetics and results of dogfish and tilapia species, the nutrients content analysis, and finally a little conclusion about this study.
This work was funded by the National Council of Humanities, Science and Technology of Mexico, and the project has 5 important objectives. One of them is trying to provide development in the communities by product preservations, by adding value on the products, and also to provide high quality dehydrated foods. Also, the project has or want to increase participations in the productive lives of women and elderly, technological development by promote designing and determining optimal dimension of requirements, and to develop care by using clean energy.
Generally, fish waste is disposed of in fishmongers. They have a wide range of vitamins and minerals and other usable substances. Unfortunately, it is a perishable food. Drying is a technique that can delay the decomposition of fish. In this paper, or in this study, we will propose to use dried fish waste to produce fertilizers to empower rural and small farmers. As you can see in the images, for the methodology, we use 2 greenhouse type solar dryers, and it features a 12 volts rear top fan operated with a 24 watts photovoltaic panel. Well, in a little resume of the methodology that we have done in the study, is that we obtained the dogfish and tilapia samples from local markets. Then we cut them into thicknesses no bigger than 5 millimeters. We take the initial weight and muster measurements. Then we place them into the chamber, as you can see in all the images. And finally, we take the weight measurements every half an hour so we can get a kinetic of the dogfish and the tilapia. For the instrumentation equipment, we obtain the humidity, the chamber temperature, the environmental temperature, and the weight of the samples, in this case of the tilapia and dogfish. For the dogfish drying kinetics, we obtained the temperature inside the drying chamber, and it was about 47.69 Celsius degrees. An average ambient temperature with 32.77 Celsius degrees, ambient humidity 45.71%, and the irradiance was 1116.3 watts per square meter. And the initial muster content of the bone was 72 grams, and the same for the skin was 70 grams water per gram SS. And as you can see in the right, you can see how we obtain the dehydrated dogfish skin and the bone.
As you can see in the first graphic, the bones drying took longer time to reach moisture content stability than fish skin. The graphic at the top left shows that bones drying took 60 minutes longer than skin, and in the right graphic you can see that the bone velocity was slower than the skin drying velocity.
Now for the tilapia results, we obtain an average dehydrated temperature of 46.32 Celsius degrees, ambient temperature of 29.2 Celsius degrees, ambient humidity with 50.90%, and the irradiance was 1126 watts per square meter.
For the heads of tilapia fish, the drying time in both dryers was very similar because even when the moisture content was much higher in the transparent polycarbonate, the velocity was at first much higher also. In both dryers, the drying time was about 11 hours. The final moisture content in the sample of the transparent dryer went from 4 to 0.6 grams of water per gram of dry matter, and the final moisture content of the sample in the smoked dryer went from 3.5 to 0.4 grams of water per gram of dry matter, and the transparent drying velocity, the higher, was 0.052 grams of water per gram per dry matter per minute, and in the smoking dryer velocity was 0.035 grams of water per gram of dry matter per minute. And with this final moisture content, it is guaranteed that there is no microbiological growth. The table shows the important minerals contents for biofertilizers found in samples of fish meal obtained in the previous experimentation. We tried to germinate 2 samples of cucumber seeds. For one sample, we used the fish meals obtained as a fertilizer, enriching the soil where it was placed, and in the other sample, we used a normal cultivation soil. The sample with fish meal germinated easily, while the other did not.
For the conclusion, according to the results, the time to conclude the solar drying of fish weight does not vary significantly in the dryers used. The results show that solar drying can be used to prepare and conserve fish waste of various types to replace the use of energy from hydrocarbons. This work aims to achieve an increase in the income of small fishermen and at the same time improve the yield in agricultural crops, decreasing the dependence on fertilizers, imports, and taking care of chemical products in the country's agricultural soils. And that will be all. Thanks everyone for your attention.